All right, so this starts now, this unit on, or mini unit, I guess, on transient problems. We'll have a few lectures where we're going to talk through problems where we no longer can assume that the temperature profile is constant in time. Everything we've done so far we call steady state, which means that the internal energy is not changing as a function of time. You solve for a temperature profile, that's your temperature profile in space in X or Y. But there's no time component to it. Now we're going to get into problems where the temperature of the body is changing over time. Internal energy then of the body has to be changing as well. So we have to include that, that term in the energy balance where we say in plus generated equals out plus stored, right? So now we're treating that stored part of the equation as well. So the way we do that, let's go through an example and so talk through some of the principles as they come up. All right, so this example is a spherical object or spherical body. It's initially in time, initially at 300 degrees Kelvin. And you see the properties there. We've got conductivity, specific heat, which is now important, and density. Okay, and it's subject to some really high heat transfer coefficient. Maybe there's some really high fluid or high conductivity fluid or something like that. And then the kind of interesting thing here is we're now assuming that this is subject to a changing temperature. Right? T infinity is a function of time. And that function is given by some third order polynomial, which plotted out looks something like this. Right? So you see this initial temperature at 300, and then as time goes on, within a sub-second, I guess, less than 1 second, you're seeing a swing in temperature, and this body is being exposed to that. Okay, so let's talk through some of the ideas that we need to think about here. Okay, so this now is, let's see, this is a 1D transient problem. So this is a 1D transient problem. Right? What do I mean by 1D transient? So typically when we talk about, okay, 1D, 2D, whatever, we're talking about spatial dimensions, spatial coordinates. So if I say it's 1D, I'm saying that there's actually a temperature profile in one of the spatial coordinates. Well, it's got to be in the radial coordinate, right? Because everything else is uniform. So there's some temperature profile in the radial coordinate, but it's transient as well. So it's a function of time and space. So we would say this is a 1D transient, and we would write it as, okay, T is a function of radius and time. The first thing we want to do, though, is come up with some solutions where it's kind of the simplest entry point into transient problems as we can get. And what would that be? Well, if we can eliminate everything but the time dependence, then that gives us kind of a foothold. So we want to make some assumption where we say temperature is really actually only a function of time. So let's imagine for this problem up here, okay, the conductivity is really high within the body. Say it's almost infinitely high. That means as I'm adding heat to the body or taking heat away from the body, it's really quickly able to equilibrate internally. And so basically it's, if you look at it relative to its surroundings, it really is just one temperature. That entire body is just at one temperature at any moment in time. Okay, so making that assumption is called the lumped capacitance. Capacitance. The lumped capacitance assumption says I have an entire body, and that body is at a single temperature at any moment in time. What do we use to justify that assumption? Well, we can go back to our friend, the Biot number. And the Biot number in this case is still the resistance that we'd like to neglect. Divided by the resistance to the surroundings. Okay. For this problem, what's the resistance that we want to neglect? If we're trying to say that temperature is only a function of time, what is the thing we're trying to neglect? Yeah, Matt. Yes, and then specifically for this problem, it would be in the radial direction. So we're trying to neglect conduction in the radial direction in this body. So here we want to compare our conduction internal, right, inside the body, to whatever what's the resistance to the surroundings. It's going to be the convection resistance, right? We didn't specify any radiation here, so it's going to be our surroundings. So just being more specific, this would be R conduction in the R direction divided by R convection. Okay. If we go through and make the evaluation for the BO number, and we find that that number is small, then we're saying that the temperature drop within the body, the difference in temperature between the very midpoint, the center of the sphere, and the outer wall, that temperature drop is really small compared to the temperature drop from the wall to the surroundings. And if that's the case, then it's a good assumption that we say that the body's at a single temperature. Okay. So how do we evaluate for this? How do we evaluate these things? R conduction. R. Well, normally, we'd say just in general, this is the distance to conduct, divided by the conductivity times the area for conduction. Area for conduction. Distance to conduct divided by conductivity times area for conduction. For this problem, it's maybe not so clear what the distance to conduct is. I guess you're conducting, certainly you have to go from the very midpoint to the outer surface, like that's as far as you would go. But if we're talking about internal energy change of this body, on average, how far does it have to go? Well, again, this is an approximate thing. We're trying to come up with an approximate number, so we don't have to be super precise. But we can say, okay, this is maybe approximately, let me write it this way. So let's approximate our distance to conduct here as L conduction is approximately equal to the volume of the body, whatever it is, in this case a sphere, divided by the surface area of the body. Right, so you have meters cubed divided by meters squared, that gives you meters. And it, for this particular example, ends up being something like, half of the radius or a third of the radius or something like that. You just go through, calculate the volume divided by the surface area, and that's a good rough approximation of, on average, how far heat has to travel for this type of problem. Okay, and then the area for conduction is going to be the surface area. Again, you can see that's an approximation, because inside the body, it's definitely not the surface area, it's smaller than that. But if you take these two numbers together and follow that approach consistently, I think that's about as good as you can do. Okay, question? You're able to make it because you have to pick an area, and that's as good an area as anything else, I guess. So you could come in and say, yeah, I'm gonna calculate some area like this. Certainly you could do that, but taken together, right, taking this approach and this approach together is usually a pretty good approximation. Okay. All right, so let's see here. All right, so let's calculate out the resistances. So we'd say the resistance for this one, where did I do that? Well, okay, let's do the resistance to the surroundings. But okay, so for conduction, we have our two numbers. You just go through, L conduction is that, surface area is that. That's the formula we're going to want to use. For resistance to the surroundings, we would say, would just be 1 over h bar times AS, right? That's the resistance to the surroundings. If you had radiation in the problem, right, you can come in and evaluate radiation. If radiation ends up being higher, if that resistance ends up being higher, then that's not important. It's sort of ignored, and you would want to just use the convection. Okay, let's keep moving here. Let's see. Okay, so for this example, what we want to do is look at how some of the properties of this body actually change the response and how it reacts to this changing temperature. So what we're looking at here is a plot which we generated with an example. Let's show you in a second. But one thing to look at is, all right, so we need a way to characterize this type of problem. Like before, we have calculated the BO number. That's kind of interesting, but it's not really a good characterization of rule of thumb how the problem is going to respond to temperature changes. So to calculate the what's called the time constant for this problem, we're going to call this tau lumped capacitance, tau LC. So tau LC is a time constant for this problem that helps us really quickly get a handle on what we think the response time is going to be. So we calculate this by the following formula. We'll say R surroundings, the resistance to the surroundings. If that's just convection, so be it. If it's convection and radiation, it'd be the total resistance to the surroundings. Okay, times C, capital C, of the object. And C of the object is equal to the mass of the object times the specific heat capacity. Okay. So this time constant essentially tells us how long it's going to take the body that we're looking at to actually respond to some change in the environment. Okay, so if tau LC, lump capacitance, is a big number, that's saying that it's going to take a really, really long time for any change that's happening to actually show up, right? You're really slowly transferring heat to this body, and maybe the body really has a lot of thermal inertia, right? Think about that. It kind of makes sense. Our surroundings high, slow heat transfer to the body, and C object is high specific heat. That's going to respond really slowly. So we might look at something here, right? This line at the very bottom. Right? We see tau lumped is 29 seconds. Well, if our period of oscillation is like less than a second, it's really going to take a long time to respond, and you see it happening there. Well, what if tau lumped is 0.29 seconds? It's about on the order of the phenomena that's happening here. We are going to see some kind of a response, but it's a little bit delayed. Well, what if the object is really, really, light, or there's not much thermal inertia there, or there's a huge amount of heat transfer to it, our surroundings is really low, then you have a low time constant. And basically you trace right along with whatever is happening in the temperature profile. So before we even get into solving the problem, we could come in here and guess, yeah, okay, tau lumped is 0.3. So I could pretty much guess what the solution is going to look like before we even solve the problem, just by knowing the time constant. So again, it's like resistances. It's a tool that you have. So first thing you want to do when you're solving a problem is calculate the lump capacitance time constant. And that'll give you a lot of information.